Hello, my name is Jan, and this video will present you my work on this year PRACE project Summer of HPC. I was given an opportunity to spend this summer in beautiful Budapest, the capital of Hungary, at an institution called NIF. NIF provides academic network infrastructure and also maintains Hungarian supercomputers. Let's talk about the motivation for our project. Graphic cards or GPUs were highly developed in recent years and they have achieved enormous computational capacity. Our project asks if this power can be used to speed up atomistic simulations. For simulating atoms and electrons, according to quantum mechanics, we have chosen software package Quantum Espresso that is created and developed by PRACE partners and freely available, and also known for good GPU support. Let me show you a simplified scheme of typical HPC cluster that consists of many powerful computers, called nodes, connected with each other by fast, expensive network. Each node tends to have multiple processors, CPU units, which are nowadays equipped with many cores. Besides this, nodes might have GPUs or other acceleration cards attached. From the code execution point of view, each node runs its own instance of program with many computational threads. Communication and data distribution is done via MPI messages. On levels that share memory, OpenMP governs its parallel usage. Accelerators run their own code kernels on data copied to their internal memory. Combining parallelization schemes and platforms is called hybrid computing. In our case, we were given an opportunity to play with 6 clusters with different hardware configuration, as you can see. Okay, move on. Here you can see that for electronic structure calculations by Quantum Espresso, there are several levels on which the computations can be distributed. Distribution among images and k-points leads to relatively independent computation pools. Distributing 3D FFT transformation for plane wave coefficients is done automatically in sophisticated topological way to minimize necessary communication. At the bottom level, Quantum Espresso can use parallel implementation of algebraic solvers. Programmers implement parallelization in several ways. If you can benefit from others' work already done, you can just use external libraries. You may use also directives for frameworks automatically generating desired way of parallel execution of your loops. Finally, for best performance, you have to code your own parallel routines. So let's look at the simplest way, at the libraries. Okay, let's rather move to hands-on. In ideal world, you can find all your software pretty installed and you can run it. Up! Maybe... Okay. We need to set up correct environment. Let's look, where is the problem? Okay. Some libraries are not found. Luckily, in HPC world, you can choose from many options. Many compilers, many Scalapag libraries, many even OpenMPI versions. Compiled with different compilers may give you different results. Many FFT libraries, many QDAC accelerators. Which one to choose? Trial and error, nothing better. If none of these works, you just have to build your own version. According to vendor, building Quantum Espresso is pretty easy. Just follow simple tutorial. They even provide you a configuration script that tries to link all the libraries automatically for you. Beautiful, don't you think? Configure successful. Okay, so let's make it. Why not? Whoops! Maybe that's because. Okay, maybe it's not so simply, but certainly we are not the first encountering these problems. According to good people on the internet, you just have to set up your environment right. In case you are trying to use Intel Phi accelerators, you maybe need also to do some black magic and bypass the running routines. But all this advice might be helpful only on specific version of hardware and software, so good luck! Well, after 4 weeks of trying, we were able to run Quantum Espresso on 4 of the 6 supercomputers we were given. If you are lucky, finally you can submit your job with your desired parameters. Successful run produces output like this. It's GPU accelerated Quantum Espresso. We can see number of tasks and way how it was parallelized. We can see numbers, see how the conversions was done. We can see the time and also profiling info about the subroutines, how many times they were called and how much time it was spent in them, and whether the job was done. Finally, we can show you some promised results. The graphs show you the time of calculation when using only CPUs or employing 1 or 2 GPUs. Here you can see the relative speedup. Speedup factor 2.5 is pretty good. Okay. Here you can see how the time of calculation scales with number of cores. Since, for our simple benchmark, it was saturated at 48 cores, running on more than 64 cores makes no sense. So we have tried different approach, showing you scaling about the number of GPUs. We employed 2 GPUs per node and only small number of cores, so one might use them for other type of jobs. You can see that it scales quite poorly, because using 30 GPUs on 15 nodes gives only 1.8 times speed up to the 1 GPU. That's pretty suboptimal. To sum it up, GPU really saves your computational time, but your compilation time, that's questionable. Thank you for watching.